This is Physics 102B at Porterville College, Chapter 16 Homework, Part 2. We start with number 55. For number 55, we have an electric field of 850 volts per meter, a distance covered of 7.5 millimeters, starting at rest, and the question asks, what is the final speed? We'll use conservation of energy, which says that the change in kinetic energy is the opposite of the change in potential energy. So we have kinetic energy is the opposite of charge times delta V. We get 1/2 mv squared equals the elementary charge E times the electric field E times delta X. And that brings us to the velocity. Is the square root of 2 times elementary charge times electric field times delta X divided by m. And we get an answer of 1.50 times 10 to the 6th meters per second. Another way this could have been done, here in the green ink, is by doing a more kinematic approach. That we think back to our kinematic equation, v squared equals v naught squared, which goes to 0, plus 2a times delta x. Replace a by Newton's second law with F over m. Then in the third line, we replace F, the force on any charge, the electrical force, is equal to the electric field strength times that charge. So now we have v squared equals 2 times the electric field times the charge over m times delta x. And that gives us, in the final line, next to the smiley face, v squared equals 2 capital E lowercase e delta x over m. And to get v, square root it, and that's exactly what we got in the first solution. Number 57. I'm paying more attention to absolute values. As I've said many times in class and in these videos, the negative sign often really just gives us information about what direction, and for this problem we don't care about the direction. So the magnitude of the electric field is delta V over delta X, so we have 250 volts divided by 6.5 millimeters, and that gives us 38,462 volts per meter. In part B, the force equals the electric field times the charge. Notice how I've changed the units. In part A, since part A was volts per meters in the units, I gave that answer in volts per meter. But just to make the units work out, dimensionally it's all the same, so it doesn't matter, but I've changed the units here, calling it newtons per coulomb, so that when we multiply by the charge in coulombs, we're left with newtons. It's 6.16 times 10 to the negative 15 newtons, and that would be femtonewtons. Number 59. The potential difference from a point charge is K times the charge divided by R, so we're solving for that charge. The charge is negative 175 volts times 0.65 meters divided by our K constant, 8.99 times 10 to the 9th. So we get a charge of negative 12.65 nanocoulombs. And regarding the plus or minus sign, since voltage is negative, that means it's attractive for a positive charge. Number 62. With the capacitor, be careful with your units on this one. The area of the square plate 1 centimeter times 1 centimeter. That would be 10 to the negative 2 meters times 10 to the negative 2 meters, and that gives 10 to the negative 4 square meters. And we're solving for the distance. So we plug in values. Distance equals epsilon naught, the permittivity of free space, times the area, times capacitance. And we get a distance of 0.3 millimeters. For part B, the capacitance has changed, and you plug those numbers in as you see in the video, as you see on the screen, and it gives a distance of 3 times 10 to the negative 7 millimeters. The question asks in part C if this is practical or not, and you have to consider 3 times 10 to the negative 7 millimeters. That's 3 angstroms, or 3 times 10 to the negative 10th. That's the typical size of a single molecule. So no, that's not really practical for a capacitor. Part A, 0.3 millimeters. That is more practical. 63 is another question involving capacitors. Here it gives the capacitance, the distance between them, and we're to solve for the area. Now the question is actually asking what is the radius of these circular plates. So without directly solving for area, I'm just directly solving actually for radius. So I convert area of a circle to pi r squared, and then I solve for r. So we get r equals the square root of capacitance times distance divided by pi divided by epsilon naught. And we get 0.028 meters, or 28 millimeters. Number 77 involves the energy stored in a capacitor, 1/2 CV squared. Plug in the numbers given, and you get for part A 648 joules. Part B asks about the power. So you take the energy you got in part A, 648 joules, divided by the time. 2.5 milliseconds is 2.5 times 10 to the negative 3 seconds, and you should get 259,000 watts, or 259 kilowatts. And the last one on part A, the last one for part 2 of this video series is number 79. So part A, we have the capacitance is epsilon naught times A over D, and that gives an answer of 4.425 times 10 to the negative 10 farads. I give these answers just to give you some practice thinking about the unit conversions with the metric in nanofarads. So remember, nano is 10 to the negative 9. So the way I think to arrive at it in nanofarads is if I want to turn this 10 to the negative 10 into 10 to the negative 9, that means I'm cranking it up, the power of 10 by 1 power of 10, which means to balance it all out, I crank this one down by a power of 10. So it becomes 0.4425 times 10 to the negative 9, or 0.4425 nanofarads. For part B, if I want to get this in nanojoules, well, nano is 10 to the negative 9. And so to go from 10 to the negative 7 to 10 to the negative 9, we're cranking this power of 10 down by a factor of 2, or by 2 powers of 10. So we balance it out by cranking this one up by 2 powers of 10. It becomes 553 times 10 to the negative 9, or 553 nanojoules. And finally, the last one is the charge. Charge equals C times V. And so we take the capacitance from part A. do it in the MKS units. So take this 4.425 times 10 to the negative 10 farads, multiply by the voltage given in the problem, and we get 2.2 times 10 to the negative 8 coulombs. Now, turning that into nanocoulombs, or 10 to the negative 9, means taking the power of 10, taking it down by a power of 10, which means we increase the coefficient 2.2 by a power of 10. So we get 22 times 10 to the negative 9 coulombs. And that's the end of part 2.